All right. Hello, everyone. Welcome to another episode of Quirkcast. This is your host, Tim.
And I'm Mikey.
And this is Sile. Welcome, everybody. I currently am not showing my face because I am in a location and it'd just be too complicated and very crowded. So anyway, so welcome everybody to a brand new episode of Quirkcast. And before we get on with the episode, just a few logistical things. If you have any questions or comments, do post them in the chat so we can get to them. And if you haven't already, do join our Discord channel. So without further ado, so I guess Mikey, I was wondering, like, there's an old quote I heard that when like you're having fun, time flies, and when you're like not having as much fun, time seems to like move very slowly. So this is like if you perceive different rates of time, does that mean it's an illusion, or is it actually something?
Yeah, I don't know. This is a question that I guess philosophers were interested in before physicists were, because our experience, the way we experience time, you can measure it in seconds, but kind of a more natural way to think about it is like the number of thoughts you can have like per second, right? Like if you can have 1 trillion thoughts per second, or if you can only have like half a thought per second, your passage through time as far as like your cerebral consciousness goes is very different, right? And I think that's a big part of the reason why time seems to fly when we're like, doing very active things where our brain is constantly alert.
So wait, one of our audience members saying cannot hear.
Oh, damn. Let me double check. 1 second.
Okay.
Maybe we can restart after this so that I can edit them.
Yeah.
1 second.
I'm saying things. Testing. Although I see the captions coming up.
You do? I don't.
Well, I mean on the Zoom here on the other side.
Yeah, I don't see any transcriptions though.
Oh, I don't think they'll be there. They'll probably be on the other computer screen.
Usually I can see them though.
It says okay. They say okay now. They can hear.
It looks like it's functional. Can someone confirm it's working right now?
Yeah, they confirm it.
Okay. Well, let's continue the discussion. We'll edit this out.
Yeah. Okay. So anyways, as I was saying, like that's a really interesting point, right? Because we think of time as something that we can measure in seconds. And a second is a notion of time that we can all agree upon. So I can measure what happens in a second. Tim can measure what happens in a second, and we can all agree on that. But it's also kind of a function of how fast your mind is moving, right? If your mind is moving like 1,000 times faster than someone else, then you'll be able to have more thoughts in the same amount of time and be more productive at that time, which is something we usually associate with duration. So there's the flow of time as far as what it takes for two people to agree, like a standardized metric that works across people. But then there's also this kind of other notion of time, which is how we experience it. And, philosophers used to find it interesting that time is the only kind of dimension where if you imagine you take away all our senses, like, you poke out my eyes, like, take out my nose, ears, like I can't do anything except exist in my brain. I can still experience time, right? But the dimensions of space will cease to have any meaning for me. So I think they believe time has a kind of special status amongst the other dimensions, which is also what physicists think.
So what you're saying is like one part of it is due to the amount of thoughts that one can have in like a given amount of time. And then
there's some confusion because like people talk about like, is time an illusion? Well, which time? Are you talking about my experience of time, or are you talking about like this notion of time called the second that we can all agree on?
I would say that there's actually multiple layers of sort of definitions of time, at least from the angles of physics. Like Mikey said, the way we experience time has to do with our interactions in the brain. So in physics, we like to talk about, how fast an interaction is, and that's usually related to some sort of a time scale, basically. So the human brains has sort of like a roughly stable rate of interaction. Like, for example, you, me, or anybody cannot distinguish things that happen. Let's say if I'm looking at the screen, I cannot see things that are happening. Let's say like 0.01 millisecond. I cannot distinguish that perceptively. It just doesn't make a difference. So it's sort of like the natural time scale of human brain interactions, just the chemistry going on and neurons firing. That's like probably like something like seconds or something, right? And it has to transmit to the body and whatnot. So
there's an exact number, right? Our brain has a refresh rate, and the screens are playing off of that to give us the illusion that it's continuous.
Yeah, and obviously, if you try to look at like a fly, I mean, they have a way faster reaction, and also they die way faster. So their perception of time, it's a bit faster, right? As we move our hands, let's say we move really fast, the fly will perceive your hand is just moving very darn slowly, so you can never hit one really. So, but in physics, I think this can be generalized. The perception of time has to do with the rate of interaction, right? And you can talk about the notion of some time evolution, right? Like how long does it take for the system to change appreciably, basically, right? And that's one notion of time. But that notion is very emergent. But then at the end of the day, it's linked to two things, right? It's linked to first the interaction strength in some ways, the type of interactions, but also it's linked to this kind of more fundamental notion of time. Because in order for interactions to happen, it has to happen across some time. And there's some more physics that kind of unravels those interactions. Like, what are those interactions?
So what do you mean when you say like the system has changed appreciably or like noticeably?
So like if I can continue with the refresh rate analogy, right? Like
Sure.
like everyone's familiar with like stop motion pictures where you make a movie by taking like a picture and then moving the dolls a little bit, taking another picture, moving the dolls a little bit, and you get this kind of like choppy kind of animation. So you can ask the question, like how many times per second do you need to take a picture in order for it to look totally smooth, right? And it turns out that our brains have a refresh rate where if something is happening on a very short time scale, it's actually invisible to us. It might as well have not happened at all. So it's like if you were going to do a robbery, you'd have to run into the bank and steal all the money quicker than I can blink my eyes, because by the time I'm done blinking my eyes, you're gone. And then it just looked like the money disappeared. So the question is, does the universe have like a refresh rate? Is there an absolute notion of time, or is it really just whatever we experience? That's the question.
That is kind of interesting. I guess, as you're mentioning, it is true that they are like discrete frames. When you play a movie, they just move really fast relative to what we're used to. So they appear continuous. I mean, isn't that like always happening when you like look around? Like if you look from the right side of the room to the left side of the room really quickly, your brain fills in this like notion of continuity, but you actually don't really see anything per se.
Yeah, I'm not an expert in psychology, and I'm sure I'm going to get butchered for this, but my understanding is a large part of the consciousness, like the idea that we experience things continuously, is in large part like the power of our imagination at work, filling in the gaps.
Yeah, I think for us, it's best to stick to particle physics.
Yeah, but I think to the extent at which that's true, in a certain sense, then time is definitely an illusion, right? If you're talking about the kind of time that we experience, then the question is time an illusion? 100% yes. So let's move on to the more interesting question.
Oh,
Yeah,
It's
but
actual time an illusion.
wait, but it's not actually 100% an illusion, right? From this argument, right? So part of that, the interaction part is kind of, you can think of it as an illusion, right? If we have very vastly different interaction rates, like the kinds of times we're experiencing will be vastly different. But let's just kind of average those out. Like let's imagine all possible types of human beings, flies, elephants, whatever, right? Or the earth, the movement of the rocks, the celestial, bodies, right? But to some extent, there's this notion that sure, time moves faster or slower, right? It takes eons for mountains to change. I mean, it takes like 100 years for a human to live through his lifetime, but it's sort of, there's this notion that they sort of kind of go in the same direction, right? Even though the rates might be a little different. So, and that kind of hinges on, I mean, sure, the interaction rates are different, right? Certain things happen faster than the other, but then those interaction happens over time. There's this sort of more general concept of time that kind of encompasses every system. And, like Mikey said, like the perspective notion of time seems like an illusion. But now what about this more general notion of time? There's this common denominator that every system has to go through. Like, is this time also an illusion, or is it not an illusion, or is there something fundamental about it? I think that's sort of the age-old question.
Yeah, and I think this is like, isn't it? So we've established that me and Tim, for example, we might experience time very, very differently depending on our mental state, right? But isn't it amazing that if we were both to take stopwatches and measure the amount of time passed and we compared, that they would agree? The fact that there is a notion of time that we can measure with a stopwatch and go to each other and have an unambiguous agreement with is actually kind of amazing, right? Because that doesn't have to be true, but every time anyone's ever done this experiment, it's turned out to be true. And it could fail tomorrow, right? Like tomorrow, me and Tim could do an experiment and measure, compare, and find that it's totally off, but it's always on point. So there's seems like this universal, fundamental, absolute notion of time that exists that kind of connects all of us to each other.
but from like a physics point of view, I thought that like your measurement of time is relative depending on the observer's reference frame, and that like if you're outside, like if you're far enough apart from each other, just that you're not like, you can't really communicate with each other via light, then wouldn't it be the case where like there's no notion of like causality, for instance? And so
Yes,
having
absolutely.
the notion of time implies some form of causality.
Yeah, it's crazy that it's set up in such a way that only communities of people who live together will agree with each other. Someone who's flying around like the speed of light this way might have a completely different notion of time, but that's not going to be an issue because they don't live in the same
community. To some extent, you can argue that we as humans, or at least this Earth system, is kind of a bunch of, it's sort of like close-ish, like we're a close-knit community who interact with each other. And in that way, our clock kind of synchronized to some extent. And like Sahil, you said, yes, time indeed is relative. And that's what makes this sort of intriguing. Like if you take Einstein's theory seriously, and you should anyway, it's a good theory, general theory of relativity. It says that the direction or the rate of passage of time is very malleable. It's like a sheet that kind of can stretch and in different ways. And there's no reason for you to ever expect in different areas of the universe that there, like locally, maybe in a small enough area that there's sort of like a rough agreement on how time is, but there's no reason why it wouldn't just mold like really in a very extreme way. Like Mikey here and me, let's say 20 miles away, there's no reason why we wouldn't have like that drastically different like feelings of time, right? But of course you can argue that maybe that's anthropic. Like if the universe is so screwed up in that way, there's so much curvature of space-time, maybe humans wouldn't have been created in the first place. It's like we need some level of stability, of some kind of like less crazy of a universe, for this level of like consistency of time to arise, and maybe that's plausible. And in some sense, like that's how a society runs, right? Like imagine we have vastly different concept of time. Like getting to work would be horrible, right? It's like
yeah, certainly a smooth space-time is a prerequisite for the evolution of life, I think.
I guess one question I have regarding that is like is like the direction of time an illusion, or like there's a sense I have of going forward, and people have different ways of perceiving it going forward, but it doesn't seem to ever go back or stay put. It just seems to keep going forward.
That's like surprisingly the more interesting and more perplexing question. I'm not sure, Tim, maybe.
I think it's I'm actually undecided. I think it could be a little bit of both. Let me just kind of wind through the arguments for both sides, okay? So you can kind of argue that maybe there is a universal direction, like a direction sort of makes sense. And then the direction could be like, of course, by direction, I don't mean like one fixed direction, just kind of like an overall flow. Like imagine like a river, like river always flow down, but the water in the river could move side to side, right? But on average, at the end of the day, they tend to kind of move down, right? And they don't flow backward. And observationally, this is roughly what we see, right? Like Einstein's theory of relativity says that, you know, the notion of time could be different. And that's already evident by, you know, things like the stars we observe, for example. Like you look at some supernova that's like millions of light years away, and it's just kind of boggles the mind when you look at the light that comes in. You're like, oh, dude, that's like, you know, that's like a few million years ago, right? Like, does it even make sense to talk about that supernova still existing or what? Like, it's just ancient light, but then how do you even talk about it? Like, what is past and future for something so far away, right? But yet you can this notion still holds, right? As we move forward, we observe the supernova process through time, right? The supernova explode, it doesn't get unexploded even for something so far away. So there seems like over the entire cosmos, even though this notion of time kind of shifts around left and right, but it does have a general direction. And that direction is forward. It's sort of average forward direction. And you can kind of scratch your head and be like, you know, where does that come from?
So Tim, I kind of want to throw you a curveball question.
Okay.
Maybe it's a huge misconception, but like, so typically in relativity, before relativity, people thought space and time are different, but through relativity, we realize they're connected. But if they're connected, like why in three-dimensional space can I go up, down, left, right, backwards, forwards, but in time I can only go like one direction? Like why is that that asymmetry? They're really like similar to each other, then if they're like connected to each other, I would expect to also go backwards in time. Like
so
I'm so glad you get it to Tim.
No, that's an amazing question. You know, in fact, this is a lot of confusion when people learn relativity as in student undergrad. It's like, oh, we keep talking space and time as the same, but like we don't see it in everyday life. Like that's the crux of the thing. Like how do I relate that to everyday life? That seems so far away, right? And it turns out the answer is cosmological, right? And the reason we do not see that is because we are stuck moving very slowly with respect to a particular sort of shape or image of the universe. And let me make that more precise, right? Like in order for us to experience different kinds of time, we have to travel like close to the speed of light. And that's how you kind of change your perception of time of me relative to you and so forth. And you can ask the question, well, how come we can't do that? Well, it takes a lot of energy. Or then you can go deeper. Well, why does it take a lot of energy? Well, duh, we have a lot of mass. We don't have all these energy freely available. Well, imagine if we were very light, we were massless, then it's much more likely that we can switch these notions of time much more easily, right? So the reason why we cannot experience those different kinds of time is because we as a whole, like, as the entire universe, we got masses, and we kind of on average get stuck on sort of this imprint, and people usually refer to as the CMB, which is just think of it as sort of like it's like in the beginning of when Big Bang happened, it made a decision and say, hey, we're gonna choose this one direction of time, and this in this direction of time, space gets bigger uniformly. Like that's the reason really why we are stuck with this sort of average notion of time, right? But it didn't have to be that way. It turns out, it's because of the conditions of the Big Bang, which picked out a direction for us.
Wait, what does multiple directions in time mean in that case? You made it sound like now you can imagine time not as one-dimensional, but two-dimensional, three-dimensional, or like n-dimensional.
Yeah, I mean, time is sort of one-dimensional, but time can mix with space. I know this is kind of hard to grasp, but space and time mix together. It's almost like imagine you're going across a river, and imagine you have some cross current. Let's say you across the river with no like cross current. You can just go straight across.
Yeah.
And if you have some cross current sweeping you, and you were swimming in the same direction,
Mm-hmm.
you're gonna go a little diagonal off, right? And it's gonna take you longer to reach across the shore, right?
Yeah.
So time is sort of like that, like if you move at different relative speeds, you get these kind of cross currents that can kind of slows you down, speed you up in some ways relative to other people. So in that abstract sense, yeah, space moving across space is kind of like this cross current that will kind of sweep, that can kind of mold that direction of time for you.
Huh. So what you're saying is I can think of this as if I'm going across a river, and the river is sort of like time. And so it may take me, quote unquote, like more time to do something relative to somebody else's reference rate.
Right, yeah. And in order for you to, let's say, like catch up to someone else's time, you have to go through space to catch it. So it's kind of like it's mixing space and time. I know it's a little abstract because like we don't tend to think of moving in time as sort of like we're doing it because it just happens. Like you have no choice.
Yeah.
but it's kind of like that. You kind of have to, it's like you're swimming across in it. It's just that it doesn't take effort, so you don't think much of it.
So are you saying it would take effort to like stay put in time, if not go back in time?
Oh, wow. I don't know if that's possible. It just,
Well, it would take Mikey, sorry.
I mean, at the risk of making this more confusing, I just can't help but want to mention like the intriguing kind of thing that if you notice that the kind of this asymmetry of time becomes more apparent when you zoom out, right? Imagine if you zoom down, like, into every single atom, into every single proton and look inside at the quarks. If you look at those processes, pretty much everything that happens forwards and backwards is roughly the same, right? You just have particles turning into other particles. And maybe in these very rare parts of the space, you have some particle that turns into another particle that can't go backwards. But the vast majority of things happening are, look completely like there's no direction of time. It's only when you zoom out and you look at the end result of these kind of things that you see that, oh, time is actually moving this irreversible direction.
Yeah, so I think this perspective mixes the two concepts basically, and they are related. The first concept is this fundamental notion of this time as a number, right? It's just things happens across time, right? And of course, you look at the physical laws, a lot of physical laws, things happen forward in time and things happening backward in time. They're exactly identical. And that's what Mikey's saying. If you zoom in on the molecular level, and in fact, you can even do it in the cellular level. I think there's you look at some of the proteins and I think ATPs or whatever, and they're like these little motors that powers our muscles and whatnot, and they're moving around. You play the movie forward and backward, no difference. You can't really tell. Like even though there is indeed this notion of like time as a number, the fundamental concept of time more going forward, yeah. But forward and backward is exactly the same, right? But then you scratch your head, well, like how come like overall there seems to be a theme of like time going forward irreversibly, right? But that's a global, macro, very very macroscopic direction, average, when you average everything out, like in the cosmos, and ultimately that averaging out, and you say, well, what is that direction? That direction aligns with the Big Bang, basically. Like the Big Bang is kind of the ultimate, the biggest ultimate dictator of this, overall flow, I guess, of time in our universe.
So hold on, at the risk of making this even more confusing, I thought even at a microscopic level, there's certain things where like time, the symmetry between going backwards and forward in times is not valid. So things like weak interactions.
Yeah, that's true. That's true. But I'm just saying that the average picture starts to go in that direction.
Okay.
I wasn't trying to make a theorem kind of like statement.
Gotcha. So then what gives? Like, is it just kind of that we can't measure things to like infinite precision? Would that solve the problem? Or like what is it about that's going like up with time? Like, why is there a direction of time is my question. At least at our level.
Yeah,
microscopically.
I think it's not so there's one way people try to explain the direction of time, and I don't think that's valid, right? And this is this notion of entropy. People say, oh, things tend to go from like less, like, what is it, more orderly to less orderly. Like, oh, the
things
plate
fall apart.
Yeah, like the plate breaks, okay? And that's why you cannot unbreak the plate, because it's hard. I don't know, it's more chaotic. But
can.
But that's a very silly argument. It is tantamount to saying, oh, if I eat poison, like I die. Oh, why is that? Well, poison, it's deadly. That's why you die. Like, that's not an explanation. That's an effect of the direction of time, right? The reason really why the plate breaks and it like imagine if the plate was already broken, it wouldn't have a chance to get broken in the first place. So this question wouldn't even arise, right? If the ice, was already melted, you wouldn't even ask the question why the ice melts in the first place, right? So if the universe was already a chaotic mess of photons, just completely uniform radiation, with no expansion whatsoever, there would be nothing for you to describe, oh, Earth, humans, and somebody putting an ice on the table for it to melt to ask this question. It wouldn't even happen, right? So the ultimate reason why things happen one way or another is because someone set it up to be this way, right? Like, you ask this question, what somebody put an ice block for it to melt, right? And you ask again, well, why did that person do that? Well, it's because he has some idea and some thought earlier, right? So you always trace it back in time, right? It's kind of the circular logic. The reason why things happen, you always go back one step ahead. And ultimately, the ultimate setup, is the Big Bang, right? Like, everything happened because of the beginning, and the ultimate beginning kind of, at least the way we think about it in cosmological terms, it's the Big Bang. So the Big Bang really set you up this direction.
Well, no, wait, Tim, I want to kind of challenge that with sort of what I commonly hear when people describe entropy. So, like, yeah, I do agree with you. If we're in a dilute gas of photons, there's no ice cube to put on to see it melt. But wouldn't that already indicate that the universe is like in a quote unquote higher entropic state, so it has higher entropy? But if you lived in a world where there are ice cubes and these sort of like plates didn't break and stuff, that would be a lower entropic world, right? And so couldn't you still make the argument from going from lower entropy to higher entropy is a notion of time itself? Or
yeah, so
the Big Bang is not a natural state, right? It's kind of unnatural in some ways.
Yeah. The whole point is the Big Bang is highly non-equilibrium. It's almost like someone really was playing this game, be like, you know what? Let's set up a universe and see what happens. Like, that's what
we're going to dangerous territory here.
Well, yeah, I mean, I don't want to link it to any, suspicious thought on.
Why not though? I mean, it's kind of like, geez, like a computer program, like when you set it up to run, right? The initial state is set up in a highly non-generic state relative to the
computer. And in fact, these entropy argument, it's completely tautological. You say, oh, you go from low entropy to high entropy. That's total. That doesn't say very much. Like, low entropy just means kind of like low entropy just means like fewer possibility. And in fact, if you look at statistical mechanics, like you could actually go from high entropy to low entropy. It's just that it's less likely. Like nobody ever says that this rule is not allowed, right? So entropy is kind of like a scapegoat. It's just a different way of reframing the problem. It actually doesn't provide an explanation. But the ultimate explanation has to do with physics, right? The way, it's the way the Big Bang is set up. Really, it's because Big Bang had low entropy. I mean, which is just another way of saying that Big Bang was set up in such a way that the universe could evolve to the way we are today.
Huh. So you're saying that it's because of the Big Bang, and it's not just because of like entropy and just by itself as an argument that entropy is increasing, but it's more of the initial conditions of the Big Bang.
Yeah, basically. So in the condition of the Big Bang has to have incredibly low entropy, and there's no particular reason why it's the case. It just is. It's just how we observe it, and this is kind of like, do we care to explain it? Because if we were to, like one way to explain why in the beginning of the Big Bang, why it has low entropy is that even earlier there was even lower entropy. Like that's one way to explain it. But of course, yeah, but there are other speculative ideas actually.
So I have another question. We on earlier episodes related entropy to information, we argued that information, at least at a microscopic level, is conserved, or at least that's what most like people in the field believe. And so if at a microscopic level entropy is not changing, does that mean at that level time even is relevant or makes sense? Or like, because we're talking as us as individual macroscopic creatures in the system as like finite observers. But if you were like the universe yourself, does the notion of time exist?
That's a very intricate question. Mikey, do you have some thoughts? I need some time.
No, I don't actually.
Yeah, well, I mean, the entropy of the universe turns out to be a very tricky concept to define, actually, because the question is, what do you consider to be a universe? Do you consider the universe to be, because the universe is infinite, first of all. You can't just be like the entire universe. I'm gonna look at things like the entropy, and entropy. The really the right way of thinking about entropy is sort of a very much information theoretic way, right? And if the universe is kind of like perfectly specified in some ways, yeah, then you can say, yeah, it has perfect information, right? And the entropy would not change ever in any way. You could argue that, but you can't do that, like because of entanglement and stuff. And the fact that it's the universe is freaking infinite, you can't just say, I can define one thing and that's the universe and that is perfect information about everything. You can't do that. You have to say the best thing you can do, maybe like you select like a sphere that has influence on each other, like a causal sphere. And you can calculate some sort of notion of entropy, the amount I mean, any patch of universe is also entangled with the outside. So in that way, you can talk about entropy. But that's a very tricky concept. So I'm actually not exactly sure how to answer that. It turns out that if you actually carefully consider all the entropy of the universe and include cosmological effects and maybe quantum gravity, it's not so obvious that it always increases.
Yeah, I think that's, we can have a whole episode dedicated to that. But I think the crux of what Tim's saying is that, when you talk about the universe, you're sort of drawing an artificial boundary around some part of space and saying, this is my universe, let's talk about the entropy here. And if you do that, then, you can pretty much cook up any kind of situation you want with entropy in that box. But that's not the question that I think we're trying to get at, right? That's kind of like a red herring in a sense, but.
Yeah, I think given the limits of time, let me just say that the second law, that entropy always increases, it's not necessarily sacred. If you put a gun to my head, be like, do you really think that's like a sacred laws of physics? I wouldn't put my money on it. I don't know. Like maybe it'll be violated. In fact, it does violate it only with low probability.
No,
And
I mean
people-
not or with high energy, right? When the plate breaks, I can put in the resources to molecularly reconstruct that plate if I want to.
Yeah, in fact, there's some crazier theories on cosmology that these are more like speculative, that the universe could go back and forth. And in some periods, in some pockets, maybe entropy could be decreasing, right? But then this is very speculative. So very tricky, very tricky, very tricky question and answer.
Yeah, I think it's difficult, and definitely I could see us going down rabbit holes. So wow, we are definitely way over time. So I think we should end on some concluding thoughts. So yeah, so Tim, do you have anything to say?
Yeah, so I guess the short answer is, it seems like time probably isn't, at least human time is an illusion, right? There's a more fundamental concept of time that our perception is linked to. And whether that's really fundamental or not, well, that's again up to debate. So very interesting question. So
Yeah.
I would say like soft yes. Yeah, probably it's an illusion.
All right, Mikey, what do you guys say?
I think the answer yes is consistent with the idea that we live in some kind of simulation inside a quantum computer. And that's always been my stance. So I'm happy with that.
Great. So on that note, I'd like to thank everybody for joining us, and we'll see you all next week.
All right.
Yeah.
Bye.
Bye.
Bye.